Thanks very much, Philip, and good morning, everybody. Let me just first start by mentioning there's going to be a fire alarm test today between now and 10 o'clock. So if you do hear the fire alarm, we don't have to get out, but I'll stop speaking for a little bit until the fire alarm finishes. So my name's Chris, and I've had the pleasure of working with many of the people in this room for a few years now on probabilistic numerics. And one of the things that I've always wondered about is the extent to which the probabilistic perspective can fully reproduce all of the power and the performance levels of, let's say, conventional numerical methods. And how much work would be, if that is possible, how much work would be required to achieve that? So that was the genesis of this project, which is a few years old now, but we've been iteratively refining these ideas. Can we come up with probabilistic numerical methods for potentially quite difficult numerical tasks in a black box way that doesn't require deriving new probabilistic numerical methods from scratch, as it were? Can we piggyback off existing work in numerical analysis? So I'm just going to set the scene by recapping the setup and notation, or approximately the notation that we saw at the end of John's tutorial yesterday. So this is a sketch of how we would construct a probabilistic numerical method for a linear numerical task using Gaussian processes. So we suppose that the state of the universe, everything that we could possibly want to know, is encaptured by a string of numbers, and I'll call these U, and they can be indexed by some index that could be discrete or continuous, depending on whether we're interested in a discrete or a continuous quantity. We're going to obtain some sort of information relating to the universe through what John was calling an information operator. This is a map, A, that takes as input the state of the universe and returns to us some finite amount of information about the universe. Okay, so concretely, I'll skip ahead to this example here. Concretely, we might be interested in the integral of a function, a continuous function between 0 and 1, but the information would be evaluations of that function on a finite grid. We wouldn't have total information about that function, just a finite amount of information. And the next ingredient is a quantity that we're interested in. So we might not be interested in the entire universe, we might be interested in a particular aspect of it, and that would be captured by this function q here, which takes as input the universe and returns to us some number or string of numbers or function or something that we're interested in. So again, for this numerical integration example, we would be interested in this function q of u, which is just the integral, understood in the basic Riemannian integral sense of a continuous function u, which we would like to approximate based on this finite information provided to us through the information operator. So that's the setup. And if we have that setup, where we have a linear information operator, then we can construct a probabilistic numerical method. And actually, we can do this even if the quantity of interest is a nonlinear quantity of interest. Here's the general recipe, which we saw yesterday. We start by positing a Gaussian process prior probability distribution for the state of the universe U. So in other words, we assume that this string of numbers that we don't know are jointly Gaussian. So if this is a finite set of numbers, we assume a multivariate Gaussian. If this is an infinite set of numbers, we'll assume a Gaussian process. And we'll model this formally by a Gaussian process. So I just used capital U there to denote a random variable that is a model for the unknown state of the universe, lowercase u. But once we've got a Gaussian model, we can condition this Gaussian to exactly agree with the information that we have through the information operator. And conditioning of Gaussian processes is nice in the sense that it's completely conjugate and explicit. So we can write down the conditional distribution for our Gaussian model of the universe, given the information that we actually obtained. It will again be a Gaussian process with a mean function and a covariance function whose form is algebraically explicit. You might require some matrix inversions. You might require applying this operator to the prior covariance function, but yeah, we can do this. And John showed you in Python how we can do this. Okay, so that gives us the conditional distribution of the universe given the information we had. If we're interested in a quantity of interest, Q, which is potentially a nonlinear quantity of interest, Well, one way to get at that is to sample from our conditional Gaussian process and then push the samples through this quantity of interest Q. Okay. That might be easy in this case. If Q is a linear function of the universe, then actually the conditional, well, I should say I'm never quite sure. So I want to talk about a marginal of the posterior. So is that a marginal of the conditional or a conditional of the marginal? Terminology starts to get really unhelpful at this point. But I've got a posterior distribution, and I'm interested in the posterior distribution of the quantity of interest specifically. So it's like a marginal of the posterior distribution. If that's a linear quantity of interest, then I can get that as, again, an explicit Gaussian posterior distribution for Q. If it's not linear, then I can sample from this, and I can just evaluate this quantity of interest on my samples, and I'll get a Monte Carlo approximation of that quantity of interest. So that's the setup for constructing a probabilistic numerical method in the case where the information that we have is linearly related to the state of the universe. Are there any questions at this point before I jump into the nonlinear case? Okay, so basically things are doable in the linear case. So I'm going to show you a problem now which looks like a linear problem, but turns out not to be. And this is apparently not such a difficult problem, but actually is extremely difficult when it comes to constructing a probabilistic numerical method. So suppose that the state of the universe is a d-dimensional vector, and we're interested in this vector itself. So our quantity of interest is this vector. But the information that we're going to have on this vector is not just directly observing the coordinates. We're going to observe linear projections of this vector. So in other words, there's a linear system of equations where we're going to observe B here, and M is something that tells us which directions we're projecting the universe into. So our information is going to be linear projections of U. We'd like to do inference about U. So that sounds like a reasonable thing to try and couch into this framework from the previous slide. We'll write down the information operator, do the conjugate Gaussian thing, and get an answer. Okay, so what is our information operator if we want to pursue this direction? Well, it depends what's in this, it depends what linear projections we're going to take. Okay. So if I looked at all of the linear projections that correspond to the rows of this matrix, then I perfectly characterize U. I solve the linear system. So that's fine if I can do that. But I'm typically interested in problems that are so complicated that just directly solving the linear system is not possible. You know, otherwise, the problem's trivial. We don't need probabilistic numerical methods. So what do people do classically? Well, classically, the dominant methodology for solving linear systems is iterative methods. And the canonical example of this is the conjugate gradient method. I won't go into the details, but the gist of it is that you get given a recipe for which directions to project the universe into. Okay? So in other words, we're going to evaluate inner products of B with certain vectors that are often called search directions. So the search directions tell us in a sort of informed way where we expect the solution U to belong to in a subspace of the ambient RD space. So the conjugate gradient conjugate gradient method provides a recipe for selecting search directions. And you can think about the information being the inner product of these search directions, which I've denoted S1, S2, S3, with the right-hand side of this system here, B. Okay. And I've not written down the recipe, but the first search direction is exactly equal to B. The next one is a cubic function of B, and the next one's the ninth power of B, and so on. So it seems natural to let the information operator be the set of these values, right? So B is nothing more than mu. So if I replace B with mu, then these things here look like they're linear functions of U. Okay. I take U, I apply M, and I project into the search direction S. So we can write down an information operator that looks like this. And at that point, we could start doing this conjugate Gaussian conditioning. But unfortunately, this doesn't work. And the reason it doesn't work is that this actually is not a linear operator, although I've written it in a way that suggests it is. The reason it's not linear is because B, these B's here, is actually mu. So this first search direction is indeed linear in U, but the next one is cubic, the next one is some high-order polynomial power of U. So unfortunately, this information operator here is not a linear information operator. And if we if we ignore that nonlinearity, we get a very unhelpful posterior distribution that's unrelated to the state of the universe in a clear way. So I've just written at the bottom of the slide, this problem is not easily fixed. I think to some extent it can be fixed, and people in Philip's group, for example, have worked very hard on trying to fix this problem. So I'll just say it's not easily fixed. What I'm interested in is not just solving linear systems like this, but potentially solving any numerical task. And I don't have, unfortunately, the brain power to derive new probabilistic numerical methods for every numerical task from scratch. So I'd like to try and avoid having to get into the nitty-gritty of numerical methods as much as possible. And that's where this black box idea is going to come in. So the aim of the talk is to construct, in some sense, an automatic way to do probabilistic numerics for a general or, say, almost arbitrary numerical task. And the idea that we're going to make use of here is that if there exists a existing classical numerical method for a particular task, such that given enough computational budget, the numerical method will give me an arbitrarily good approximation to the thing I'm interested in, then I can couch the numerical problem as a prediction problem. I can try and predict what this numerical method will do in the limit of an infinite computational budget. Where's my data coming from? Well, I'm just going to run the numerical method at a small budget, a medium budget, a slightly bigger budget, and I'm going to try and extrapolate that sequence of approximations to the limit of infinite computation, right? So it's a prediction problem. And we know how to do prediction because we know how to do statistics. So we should be able to just lift methodology from statistical regression into the numerical analysis domain. And for concreteness, I'm going to do everything here with Gaussian processes because that's thematically consistent with the workshop, and it also makes the maths a bit easier. So this just contrasts this approach to what you've heard about predominantly on day one, which I'll refer to in a... I don't mean this to be disparaging, but I can't think of a better name, so I call this standard PN. So compared to standard PN, one of the advantages of this black box approach is that it is applicable to situations where you've got nonlinear information. Because you're actually just going to work with the output of existing numerical methods, you're going to condition on exact function evaluations, as it were. So the nonlinearity is hidden from you in this approach. In principle, you should be able to achieve performance that's consistent with the state of the art from standard numerical analysis if you take this approach, right? You would hope that if you've run a standard numerical method, you've got an approximation, then by doing some sort of prediction, you're not going to do worse than the data you actually use to make the prediction with. So in principle, at least, we should be able to get the state-of-the-art performance within a black box probabilistic numerical framework. One of the arguments that I'm going to make, which hopefully is more convincing to some of you in the audience, is that there's theory that supports this idea. And we can talk about the consistency and so on of these methods. But there are downsides as well. So if we're going to predict the limit of a sequence of numerical approximations, then we need a sequence of numerical approximations. And that necessarily entails running a numerical method more than once, because I can't extrapolate from one data point, right? I need at least two, and ideally a few more than two in most situations. That being said, though, if the numerical method that's providing me with my data is an iterative method, in any case, then I'll get a sequence of approximations for free from one run of the numerical method. So there are situations where this isn't a problem. And I have to work a little bit harder statistically, because what I'm building here is, in some sense, a statistical model for the error of a numerical method and how that numerical method should converge in the limit of infinite computational budget. So there's a bit more required from the statistical point of view. And there's a close connection between what I'm going to talk about today and extrapolation. So extrapolation is something that we're all familiar with from machine learning, for example, where the generalization, the out-of-sample performance of a machine learning algorithm depends really intimately on how well it extrapolates outside of the region where there's training data. But extrapolation is also a very classical issue in numerical analysis. And in fact, there are techniques, and the most famous of these is called Richardson extrapolation, that take as input simple numerical approximations and try to extrapolate them to get a better quality numerical approximation. So I'm going to very abstractly define an extrapolation method now, and I think this will capture most of the things that we're going to be interested in. So forget about numerical problems for the moment. Suppose that we've just got some function f that takes as input either a number or a vector of numbers x. And we're interested in the value of this function f at 0, so when that vector of x has all of the entries equal to 0. But suppose, to make this an interesting problem, that I can't actually evaluate this function unless the entries of x are all positive. Okay. So you might have in mind here that we're interested in the solution of a differential equation, but we can only work with a finite positive time step. Right? We can't take the time step equal to 0 because we don't have computational resources to do that. So we're interested in predicting or extrapolating to the limit when x equals 0. And we're going to assume that when the components of x get close to 0, the computational cost associated with evaluating this function increases. Right? So that sort of makes sense in the motivating example. There's lots of examples and applications that fit into this scenario. So maybe one of the easiest to see is finite difference approximation. If I've got a function that I'd like to take the gradient of, but I don't have the analytical gradient available, then I can just evaluate that function at two very close points, take the difference and divide by the distance between the inputs. Right? That's a finite difference approximation to a derivative. And that fits into this framework here, where x would be the separation between the two locations on which I'm evaluating the function. I'd like to get the gradient, which corresponds to taking that x to 0, but in practice I can't do that. Numerical integration, well, x could be the distance between the nodes on which I'm evaluating the integrand before constructing my Riemann sum, for example. So then the integral would correspond to the limit of infinite computation, where I evaluate the integrand everywhere. But for practical purposes, I work with a finite grid, and that would correspond to values of x that are positive. Okay. I've already mentioned the numerical solution of differential equations, but actually, these are all sort of very standard numerical tasks, but the extrapolation setup here also admits really quite complicated scientific codes, right? So you can imagine writing down a simulator for, well, rather than invent an example, I'll mention at the end of this talk, there's going to be an example of a model of the human heart, which is very complicated. It's got lots of moving parts. And because it's got lots of moving parts, there's lots of different numerical approximations that are introduced to just simulate from this model. We're discretizing space and time, simplifying some aspects of the physiology, for example. So in that case, we'd have a whole vector of things that that correspond to discretization parameters, let's say. We'd have a spatial mesh width, a time step, and a whole bunch of other things that we can collectively denote as x. And we're interested in actually the mathematical model. We're not interested in the approximate computer model. So that would correspond to predicting the output of our simulator when all of these aspects of discretization are removed. So when that vector x goes to the 0 vector. So there are a bunch of solutions to problems that fit into this category already. If we think about these classical numerical tasks, then the most famous approach to extrapolation is called Richardson extrapolation. And I think on the next slide I'll introduce Richardson extrapolation from scratch. But in a nutshell, this applies to univariate x, and it's theoretically motivated. So if we know something about how quickly this function f converges to its limit at 0, then Richardson was able to prove that by being clever about how you do the extrapolation, you can actually get faster converging approximations to f of 0 if you're prepared to get more than one evaluation of f. Right? So if you take 2 evaluations, then you might get an extra order of convergence. I'll explain that in a second. Richardson was the first and arguably one of the most popular extrapolation methods, but there's a whole literature called extrapolation methods in the numerical analysis community. And I characterize this broadly as being numerical analysis informed. So in other words, some numerical analysis is required to understand this function f before picking up and using an extrapolation method. And as I mentioned, they're typically for univariate quantities of interest. On the other side of the spectrum here, we've got an area of applied mathematics and uncertainty quantification called multi-fidelity modeling. So the idea in multi-fidelity modeling is you've built a very complicated simulation, say of the human heart. But for computational purposes, you actually run faster, cheaper simulations with a more approximate model. So that model might just ignore some of the physics. It might use very coarse spatial meshes, or it might use a very large time step, for example. But by doing quick runs with an approximate model, you can very quickly rule out, some scientific parameters that are inconsistent with your data or this sort of thing. That's an area called multi-fidelity modeling. The key points in multi-fidelity modeling is that people try and do this very flexibly, and you typically are unable to exploit numerical analysis because these models are so complicated that they're beyond the limits of a tractable numerical analysis. Okay, so let's talk a little bit more about this thing here, Richardson extrapolation. So Richardson extrapolation was an idea that is at least attributed to Lewis Fry Richardson. And I like to put his picture on the slide because he was born in Newcastle. So this is a little advert for Newcastle here. And the idea is very simple, actually. So the premise, the ansatz of this, is that we assume we can write the output of a numerical method as the sum of a few different terms. Okay? So the first term is going to be the quantity that we're actually interested in, f of 0. And then the rest of this is going to be like a first-order Taylor expansion. So we've got some correction, first-order correction, that comes from the fact that f of x is typically not equal to f of 0. There's typically an error that increases at least linearly when we're locally very close to 0. And then some higher-order error terms that come from the remainder term, the Taylor expansion. So if we have a first-order Taylor expansion of this kind, then what Richardson showed is we can combine two evaluations of this numerical method and get an approximation that's an order more accurate than the original numerical method. And here's how you can see it. This is going to be the linear combination of approximations that we're going to use. So I'm going to run f at the input x, and I'm going to run f again at the input 2x. And typically f of 2x will be cheaper than f of x because this will correspond to like a bigger step size or a coarser mesh or something like this. And if I take this very particularly weighted linear combination of f of x and f of 2x, then what happens is that the leading order error term in the Taylor expansion just gets cancelled out. So here I've got two copies of the Taylor expansion for f of x, minus one copy of the Taylor expansion for f of 2x, but you can see I've got a multiple of 2 on f prime 0 of x, minus a multiple of 2 of f prime 0 of x. So that leading order error term gets cancelled. And what I'm left with is an approximation that's provably second order instead of first order. So this thing here now is equal to the quantity f of 0 I'm interested in, plus a second order error. So that's quite neat, right? And it didn't require a particularly long derivation to do this. And the idea generalizes. So if instead of having two evaluations of the numerical method, I have s evaluations, so s additional evaluations, so s plus 1 evaluations in total, then I can take a linear combination of these s plus 1 evaluations and get an approximation to the quantity I'm interested in that is s polynomial orders more accurate than the original approximation produced by f of x. So that seems really surprising, I think. And it shows you that at least if problems have this regularity, it's very easy to exploit it in some sense. So we'd like to build on this idea. But we'd like to do it within the framework of PN. So my goals are actually a bit more than the stated goals on this slide. Not only would I like to solve general problems using probabilistic numerics, I'd also like to be able to do something like this and prove that when we do this predicting or extrapolating the limit of a sequence of numerical approximations, I'd like to be able to prove that we can do this really efficiently, ideally with more accuracy than we get just by taking the highest fidelity simulation. So unfortunately, I have to admit that Lewis Richardson was not the original inventor of this idea, although it does have his name attached to it. So the originator was Christian Huygens, who's a Dutch polymath. So small caveat there, but we'll call it Richardson extrapolation because everyone else does. So, okay, what problems are we solving? Well, I can't just use Richardson extrapolation. Well, I could, but it wouldn't provide me with probabilistic uncertainty quantification, and that's the whole aim of this talk, is to have a probabilistic perspective on general numerical tasks. There are methods that provide uncertainty quantification. Broadly speaking, they're called multi-fidelity modeling methods, but the trouble with these is they don't exploit any numerical analysis. So in particular, they wouldn't be able to give you this high-order convergence rate that you get from Richardson extrapolation, which is a bit of a shame. And neither of these existing methods that I've mentioned tell you anything about how to design the experiments that you actually run. So I need some data from which to do this prediction or extrapolation, right? But I don't know, using these methods, which values of x, with respect to x, to actually run the method on. But if I have a probabilistic perspective on extrapolation, then that should give me criteria for experimental design. So I should be able to use a probability distribution to design a collection of inputs x1 through xn, so these are all vectors, that is well suited to predicting or extrapolating the limit of the sequence. So that's one of the important goals that I'm aiming for here. So in a picture, this is what we're going to try and do. On the x-axis here, I've imagined that this input here, x, is a scalar. On the y-axis, the quantity that I'm interested in is imagine that's a scalar as well, f of x. I'm going to generate some data by evaluating this function f at some inputs, xn, represented by the red circles here. So I've got 5 data points here. The true function f is depicted by this blue curve here. What I'd like to be able to do is extrapolate to approximate the value of this true function at x equals 0. That's indicated by the blue star here. I'm going to do this in a way that provides uncertainty quantification, and it's going to be couched in the Gaussian process world. So what I'm going to end up with is a Gaussian process mean function here and credible intervals that provide me with a probabilistic prediction concerning the value of f at 0. And with luck, this prediction should be more accurate than just taking the highest fidelity data point that I have. So this is the Richardson idea. And with luck, the credible interval that I get should be meaningfully related to the size of the error between the mean of this Gaussian process and the true value of f at 0. Any questions before I delve into the inner workings of this? Yes, please.
So this doesn't take into account the approximation error of the numerical method, right? Because I thought that was the idea of probabilistic numerics.
So in this scenario, you have a numerical method, and I can ask you to give me an output from your numerical method at different values of x. I'm going to build a model which acknowledges that what you tell me is not f of 0, but it does this in a, let's say, a somewhat generic way. It doesn't delve into what's inside your numerical method. It doesn't try and perform numerical analysis on the inner workings of your numerical method. So it does acknowledge that there is numerical error, but it doesn't try and analyze it in fine detail.
So let's say I would apply this to maybe a linear system or something, or discretization of a PDE. Is there a known relation to multi-grid methods? Because it's a linear combination of solutions at different scales, or approximate solutions at different scales, which smells a lot like a multi-grid method where I add up solutions from different coarse meshes, basically.
Yes. Yeah, there's definitely the same flavor of it. So the way you'd map that problem into this framework is to say, x is something like the size of the mesh, right? So the distance between the mesh points, for example. So the performance of this method is probably going to be better if the meshes are nested, because then you end up with a sequence that converges in a smoother way to the limiting thing. And that's one of the ideas in multigrid, is that you have this carefully nested sequence approximation. So there's a lot of related ideas. But what I'm shooting for here is a totally general setup. So ideally it would be applicable to PDEs, but rather than going into the inner workings and constructing different grids and stuff, I just take the output of, say, a multi-grid method and then just use that directly. Yes, please.
Is f always a scalar quantity, or could it also be like a multi-output? I mean, it feels like this generalizes also nicely to sort of multi-output, whereas
yes.
the Huygens approximation maybe doesn't scale.
Yes, yeah, that's a nice point. Thank you. Yes, so I can get this to work for even infinite dimensional output. I'm going to show a picture, but not really talk about any of the details. But it'll be towards the end of the talk. Yeah, thank you. Okay, so let's have a look at how we can do this. First of all, I think I'm just going to try and convince you that this is a useful idea by showing you a worked example. And then if you sort of are willing to then take it on trust that there are other examples as well, I'll go into the theory and how we can justify this from the perspective of convergence orders. So what are we actually going to do? So we're going to assume, at least to start with, that we know something about how this sequence converges to f of 0. And the way that I'm going to exploit this information is by saying that, let's suppose we've got some function b such that this equality holds in the limit of small x. Okay? This is saying that we know some bound on the error that holds in the asymptotic limit when x gets very small. Okay? Later I'll come back to the situation when you don't have a bound available like this, but for now let's just suppose that we have such a bound. And of course this bound should satisfy b of 0 is 0, because when x is 0, f of x is equal to f of 0. So that's going to be our starting point. And what we're going to do is build a Gaussian process regression model that's aware of this error bound. The way we do that isn't terribly complicated. What I'm going to do is use a Gaussian process model that here has a 0 mean and a covariance function k that's constructed in this very particular way that involves the error bound that we suppose we've got access to. So there's the sum of two things here. There's a global scaling constant sigma squared, which is going to be a hyperparameter that we use to calibrate the level of the uncertainty. So we'll come back to that later. But inside the curly parentheses, we've got the sum of two terms. The first is going to just be a constant. I'll discuss that in a second. And the second is this thing here. So KE, this is going to be a covariance model, but in effect models a normalized error of the numerical method. And I'll come back to that in a second. But we can imagine that KE is just some generic covariance function, like a Gaussian or a maternal, or one of these sort of translation variant generic covariance functions. But this is going to be pre-multiplied by the error bound b when the input is x, and the error bound b when the input is x prime. And why have we set it up in this particular way? Well, we set it up in this particular way because this ensures that samples from the Gaussian process converge at the same rate as the stated error bound. So if I sample from this Gaussian process, then the difference between g of x and g of 0 will again be order b of x. So this property that we knew about f has been encoded into the Gaussian process. So once we've got that regression model that is now numerical analysis informed, we can train this regression model by just conditioning on data in the usual way. So I take some data, which in this case is evaluations of the function f for different inputs xi, condition my Gaussian process. Let's call this a numerical analysis informed Gaussian process. And that will give me a posterior distribution for the whole function, and in particular, a posterior marginal distribution for f of 0, the thing that I'm actually interested in. Okay. So as you can see, this was all simple algebra in closed form, and we've avoided nonlinear information by only working with the output of an existing numerical method treated as a black box. So in that sense, our information operator here is actually linear information, which allowed us to do this. What about this term k0? Well, if you think about the meaning of k0, let's set x and x prime equal to 0. Well, then b of x and x prime will both be 0. So then k of 0, 0 is sigma squared k0 squared. So this is basically the prior variance for f of 0. And typically, we won't know in advance of running any simulations what the likely values of f of 0 are. So in sort of standard Bayesian regression, we'd like to put an objective or a flat prior on f of 0. So what that would correspond to here is taking the limit as k0 goes to infinity, as our prior variance goes to infinity. And you can do that, but you can't do it in the prior, because then you'd have a meaningless prior. So what you do is you work with this covariance function, get your posterior, and then take the limit of k0 going to infinity in the posterior. And that gives you a well-defined posterior. It's very similar to what people do in objective Bayesian inference, where you can have an improper prior, but still a proper posterior. So if you do that, you get some nice, simple formulae. So the conditional distribution of f0, given the data, given the sequence of evaluations of f, is normal, in the case of a scalar quantity of interest, whose mean is given by this ratio here, and whose variance is given by this thing here. So I've defined everything in this expression apart from two terms. The first is this kb. So this kb is a matrix containing the evaluations of a kernel, which I'll call kb, which is just this object here. Okay. So it's this part of the covariance function. k0 has vanished because we've removed it by taking this flat prior limit. And the posterior variance, well, this will just scale by sigma squared. And sigma squared is something we're actually going to estimate. We're going to treat sigma squared as a hyperparameter of the Gaussian process and estimate it in order to calibrate the size of the uncertainty to the scale of the problem. So sigma squared n of f will be an estimator for sigma, which I'll define later. So in a nutshell, we've got a very simple set of equations here. So given a sequence of convergent numerical approximations, I can compute these numbers, and that will give me a point estimate for f of 0 and something to construct a confidence interval or a credible interval. There are matrix inverses here, which sometimes would cause people to panic, but actually we're typically going to work with n being 5, 6, 7, very small numbers of evaluations of a numerical method. So these matrix inverses here are really nothing to get alarmed about. Any questions on the methodology? Yes, Han?
I'm sorry, you might have explained it and I missed it. Can you explain how do you only work with linear information? Is that assuming linearity with f somewhere?
So my Gaussian process is on f, and I'm observing f pointwise. So in that sense, my information operator is just a pointwise valuation of f. Yeah. So I think what I've done here is I've set up the prior in such a way that the information I'm going to get is linearly related to it. If I'd opened the black box and tried to put priors on some of the things inside it, then what I would have ended up with would be something that's non-linearly related to the output.
And is the quantity of interest that you have that's already been baked into f? Is that implicit?
Yeah, so that's f of 0. Yeah, exactly. Okay, so let's see an example. I'm going to illustrate this on a problem for which, as far as I'm aware, but please tell me if this is not the case, there aren't probabilistic numerical methods for. So I wanted to emphasize that we can solve problems that have not yet been solved in probabilistic numerics. This is going to be an eigenvalue problem. So suppose that we're given a matrix A, we're interested in the eigenvalues of that matrix. And of course, there's very many classical numerical methods for this problem. Just to make sure we're on the same page here, an eigenvalue is a real value, lambda, that satisfies this equation here, the eigenvalue equation, for some vector v. So all such matrices have eigenvalues, and I'll label those lambda 1 to lambda m. And of course, eigenvalues are very important. I don't know if I need to say too much about this, but eigenvalues are widely used in really important applications of machine learning and computer science. So you think about web search engines, for example, data analysis. They're used everywhere. And one of the most standard algorithms for calculating eigenvalues is something called the QR algorithm. I won't go into details because, well, actually, the QR algorithms that get used in practice are much more complicated than what I've got on the board. But the basic idea of the QR algorithm is to iteratively compute decompositions of matrices into products of orthogonal matrices and upper triangular matrices. You do this many, many times, and it can be proven that the diagonal of this matrix AK converges to the set of eigenvalues. So I won't get into why this happens, but this happens, and this is a numerical method that you can use. And what you'll get out is a point estimate for the eigenvalues of the matrix. And that estimate will converge in the limit of taking more and more iterations of this QR algorithm. Okay, so we're going to see if we can piggyback on the QR algorithm. This is an iterative algorithm. So what I'm going to do is say, let's run 100 iterations of the QR algorithm. That will provide me with a sequence of 100 training data points corresponding to different numbers of iterations of the numerical algorithm. And I know that this sequence will converge to the set of eigenvalues in the limit. So let's try and do this black box probabilistic numerics. Now, of course, if I just try to, if I try to approach this from the standard probabilistic numerics way and sort of work out where the error is going at each step of the calculation of the QR algorithm, that would get very complicated very quickly because we're talking about matrix decompositions, and these are very multivariate things that are difficult to deal with. So let's try out this algorithm on a toy problem. This is a toy problem where we actually know the spectrum. We know the eigenvalues, so we can benchmark how well we're doing. This is going to be our matrix A, whose eigenvalues we're interested in. It's a block matrix where these blocks here are just negative identity matrices, and the diagonal consists of blocks that have this form here. And this comes from finite dimensional discretizations of a Laplacian operator. But we know what the eigenvalues are going to be. How do I couch this in the general setup? Well, what I'm going to do is I'm just going to define xn to be 1 over n. So I just need x to be something that indexes the convergence of the sequence of numerical approximations. So as n, the number of iterations of the QR algorithm goes to infinity, the sequence converges. So xn will converge to 0. So that's a sort of arbitrary choice, but it will work. What is my output of the numerical method? Well, the QR algorithm produces a sequence of matrices whose diagonal elements converge to the eigenvalues. So what I'm going to take as the output of the numerical method is the entries of the diagonal of this matrix. And I'm going to just treat these independently, which might be a little bit naive, but seems to work okay. So what I'm going to do is I'm going to, first of all, perform black box probabilistic numerics for the largest eigenvalue, and then the next largest eigenvalue, and so on. The order of convergence of the QR algorithm is actually very difficult to know in advance. So it's very difficult to write down that bound B. And the reason is the order of convergence will actually depend on the eigenvalues. So if you don't know the eigenvalues, you won't know the order of convergence, and the whole thing is circular. So what we're going to do here is go one step beyond the methodology on the previous slide, and we're actually going to estimate the order of convergence at the same time as fitting the regression model. And we're going to do that by treating the order of convergence as an additional hyperparameter, which is actually very easy and natural within the Gaussian process framework. So instead of positing a function b, the error bound, I'm going to say, well, this function b takes the form of x to some power. I'm going to learn that power as a hyperparameter. And here's what we get. So if we take a look on this left panel to start with, you can see a whole bunch of different GP fits, but each fit corresponds to one of the eigenvalues. And if we just focus on one of them, let's say this top one up here, then we can see as we run more iterations of the QR algorithm, the numerical approximation is converging to the true solution, which is this star, and the Gaussian process is extrapolating quite reasonably to that star as well, in the sense that the mean is shooting towards where that star is, and the credible region, this is the 2 standard deviation credible region, seems to contain the true solution. So the credible region is related in some sensible way to the actual numerical error. But look, if you just took that highest fidelity approximation to the eigenvalue and stopped, that would be much worse than what you get by extrapolating, because it's not making use of this sort of linear trend here. So extrapolating is actually adding something on top of the usual QR algorithm, as well as getting the probabilistic uncertainty quantification here. If you zoom in, you can see sort of things are working well. So this is a harder problem now, where we've got a bigger matrix. We take more iterations of the QR algorithm, but still the extrapolating seems to be working very nicely in this regime. We didn't need to spend any more computational resource compared to just running the QR algorithm once, because the QR algorithm gave us the sequence of training data. So that was very nice in this case. And the overhead due to fitting the Gaussian process was negligible, because the number of training data was relatively small. So this is what I'm hoping you'll see as a success case for black box probabilistic numerics. We took a problem for which there were currently no probabilistic numerical methods. We couched it in a black box way in a setting where we could automatically get uncertainty quantification. And not only that, we actually got more accurate approximations than the standard QR algorithm would have given us. We did that without doing any numerical analysis. We estimated the order of convergence as part of the GP fitting, and that all worked. Any questions about this example? Yes, please.
So you're using this improper prior, which is the reason because this is black box, or am I missing something where is there a reason why you would come up with another prior?
So when we were developing the black box methodology, we wanted to make it as generic as possible.
Right.
In this specific example, I think you could probably think long and hard and get a more intelligent prior. We almost did this because there's some results in random matrix theory that say, if your matrix has sort of certain properties, then the spectrum should be sort of like this. But the challenge with that is as soon as you start to think more carefully, then you start to think, well, actually modeling these eigenvalues as independent is probably not a good idea. So then that starts to make the methodology more complex. So we basically stopped. But I think in principle you could do that. Yes, Mike.
Yeah, you said that to choose this PP of x, this is so you model this as kind of polynomial x to the power of something and then choose this one. Right? So can you explain a bit more about this procedure?
Yes. So I'm just trying to remember if I've got a slide on this or not. I don't think I have a slide on it. So the exponent of x, so the order of convergence, is jointly estimated with the other kernel parameters, so let's say the length scale parameters and the amplitudes and so on. The way we actually do that is almost marginal, like maximum marginal likelihood. I say almost because we don't have a likelihood because of this improper limit. So actually what we're doing is the next best thing is a maximum quasi-marginal likelihood. But that's what we do, and empirically at least it does seem to work. I know that you've got a talk specifically on this issue later in the workshop, so it'd be good to maybe chat about better ways to do this as well. Okay. So I just wanted to emphasize the importance of using the Gaussian process constructed in the way that we did, which acknowledged the convergence of the underlying numerical method. So if I just used a generic Gaussian process to fit these data, I wouldn't have done so well. So what I've done here, for comparison, is I've fitted the same data using a Matern 1/2 model. So the Matern 1/2 model is what we use when we typically don't have very much understanding of the thing we're modeling, because it allows for a certain amount of roughness of the underlying data generating function. And if I do that, what you'll find is that the extrapolation is very poor, right? It doesn't make use of this linear trend at all. It just says the limit should be somewhere in the region of the last training data. So it really matters how you set up the Gaussian process. And if you set this thing up in a non-numerical analysis informed way, it probably won't work very well. Just because we've discussed it, these are the estimated convergence orders that we've got for this particular example. So they're quite close to 1. And that seems to be borne out in these pictures, right? Because there's a sort of a linear trend, right? This sequence of data is sort of linearly converging to f of 0. So these exponents are sort of being sensibly estimated, I would say. Okay, so that was the setup and some motivation. I'd like to now try and convince those of you in the room that are more theoretically inclined that this is a sensible thing to do. So to do some theory, I'll need to set up some notation and some ideas. So please bear with me for a minute or so while I do this. So recall that our starting point is going to be that there's some error bound B for which f of x is equal to 0 plus order of B. I'm going to train my Gaussian process on data x1 through xn that, without loss of generality, are going to be in this d-dimensional hypercube. So I've got d different components of x that might correspond to time step sizes, mesh widths, all of the different discretization parameters of my code. And I might as well assume that these are in 0, 1D because I've set this thing up so that what I'm interested in is the scenario where the components of this vector x are just 0. So I'm going to have data that are hopefully close to 0, and I'm going to be interested in what happens as x goes to 0. So here's a picture in 2 dimensions. I've got, let's say, a time step size, a spatial mesh width. My training data correspond to runs of a simulator at different combinations of time steps and mesh widths. I'll call those x1, x2, x3, and so on. And you would expect that the best approximation is going to be provided by this experiment down here, which is closest to the vector of zeros. So if this x1 corresponds to a time step and x2 corresponds to a spatial mesh width, then this would have the smallest time step and the smallest mesh width, and therefore you'd hope it would be the most accurate numerical approximation. I'm going to introduce a quantity called the box fill distance. The box fill distance says how gappy is my experimental design. So what's the size of the biggest box that I can squeeze into this picture that doesn't contain any of my experimental design points? And so I'm going to define error bounds that involve in some way this box fill distance. And of course, if I've got more experiments, if n is larger, then I'll have more black dots in this box, and it'll be harder to squeeze in a box that doesn't contain any black dots, and therefore this box fill distance will shrink. Okay. I think yesterday John had a very similar idea, but it was with balls rather than boxes. Boxes are slightly better adapted to this problem because the problem is defined on a box. Okay. What I'm going to do is consider a limit where all of these design points here get shrunk towards the origin. So what I'm going to do is I'm going to take each of these points and I'm going to multiply it by a scalar h. So this point in the top left corner, which was 1, 1 initially, is going to move to h. And everything else is going to scale in the same way. So I'm going to consider a scalar quantity h, which controls how close my design set is to the origin. I'm going to be interested in how my Gaussian process approximation of f of 0 can, how good it is as h converges to 0. So that's my theoretical setup. Are there any questions about this before I present the result? Okay, so here's the result. I can always go back to this if people have questions. So just to do the bookkeeping here, we're going to assume here that the error bound b is a polynomial function of order r. And we're going to assume that this generic covariance function ke has at least s derivatives in both of its arguments. I'm going to use the same notation that I did before for the posterior mean, but I'm just going to include a superscript h to show the dependence on this scaling h that I've introduced. So this is our approximation of f of 0. I'm going to start using the name I've used on the slides now. This is what we're going to call Gauss-Richardson extrapolation. It's clear why Gauss is there. Why Richardson? Well, Richardson extrapolation was based on Taylor approximations, which are polynomial. And actually, all of the theory that we do, which I won't show you, is based on Taylor approximation as well. And therefore, it seems sensible to have the name Richardson in the name. So Gauss-Richardson extrapolation. This is our Gauss-Richardson extrapolation estimate of f of 0. And it's based on training data that are this set of black dots scaled by a global scaling h. And here's the main theoretical result. We have a bound on the extrapolation error, which depends on a few different things. There's a constant here, the box fill distance, a norm, a particular norm of the function f that we're interested in regressing. We've got a term here. Let me start here. We've got a term here which corresponds to the supremum value of b over the shrunken hypercube whose side lengths are h. Right? So this is basically the error that you get by using the numerical method without doing any kind of extrapolation. So given the training data, this is the best approximation that you'll be able to get just by using the training data without extrapolation. But what we've gained here is an additional s orders of accuracy as a result of doing the extrapolation. So in the eigenvalue example, where we had a sort of linear convergence to the quantity, in that case, s would be 1, and we would have gained 1 order of convergence on top of what we get from using the numerical method on its own. So this result here holds when the box fill distance is small enough, and I'll come back to that in a second. So there's lots of remarks that I want to make. I'll make the remarks, and then if anything remains unclear, then let me know. So the proof for this follows a reasonably standard structure that's been popularized by Holger Wendland in this 2004 textbook on scattered data approximation. And it's based on an idea called local polynomial reproduction, which is a fancy way of sort of saying you approximate things with polynomials. And because of that, that's actually the reason why we're assuming the error bound is the polynomial up here. That was a necessary part of our argument. Is that a limitation? Well, it is. But on the other hand, if you've got an error bound that's not polynomial, you can always bound it by a polynomial. So you can always use this Gauss-Richardson methodology, even if you have to use an upper bound on your ideal error bound. What about this norm here? Well, this is saying that this result only holds, right, when this norm is finite. Because if this quantity here is infinite, then this is a meaningless error bound. So what does it mean for this norm to be finite? Well, it means that this normalized error here has to be an element of the reproducing kernel Hilbert space corresponding to this kernel up here. So that's the applicability criterion here. If I look at this normalized error, then provided that b of x is actually like a valid error bound, then this function here is at least well defined. And if it's regular enough, meaning it has sort of, say, 2s smoothness, it will be an element of the reproducing kernel Hilbert space that corresponds to that. So if my original numerical method had order r accuracy, and we've gained an additional s orders of accuracy, then we're extrapolating with an error that's now order of s plus r. That's a polynomial acceleration. And it relied on having polynomial smoothness of this normalized error. But actually, if this normalized error is infinitely smooth in an appropriate sense, then we can get error bounds that are not just polynomial, but actually exponential. And we can have an exponential acceleration rather than just polynomial. Okay, so what does it mean for the box fill distance to be small enough? What we actually need is this condition here. So rho of xn is the box fill distance. We need this to be smaller than the reciprocal of some constant that's dimension dependent multiplied by r plus 2s. So r is the polynomial order of the error bound, and s is the smoothness of this kernel here, which basically controls how much acceleration we can expect to get. There's a pretty bad dimension dependence in this result, but you've no reason to expect we could solve for recursive dimensionality. That's going to be here somewhere. It also loses something compared to Richardson extrapolation. So one of the really nice things about Richardson is that if you've just got this one-dimensional problem, then if I take one extra evaluation of the numerical method, I get one extra order of convergence. And this thing repeats. So if I take two extra evaluations of the numerical method, I get two extra orders, and so on. So it's really a one-for-one trade-off. If you run your numerical method one more time, you get an extra order of convergence. And we've lost that slightly, because if we want to get an extra order of convergence, we might have to run 3, 4, 5 extra simulations. It's not one-for-one anymore. And that's probably to do with the looseness of the arguments that we've used to get the error bound. But nevertheless, you can get that convergence. You just need slightly more runs of the simulator to do it. So the way to interpret this result is you first take n to be big enough that this fill distance requirement is satisfied. So that might be 4 or 5, for example. And then this order of convergence holds as you vary h and send h to 0. Okay. Are there any other questions about this result before I move on? Yes, Hannah?
The Richardson argument is based on a one-dimensional function. So if you were, and so this one order, for example, that idea is in the one dimension. If you're in higher dimensions, is it clear that one should expect that to be true as well?
No, that's a good point. So I didn't explain that very well. So what I was trying to contrast was Richardson in 1D, because Richardson is 1D, versus what this would do in 1D as well. So in 1D, this dimension-dependent constant here just becomes 2. But we still have a requirement which is stronger than Richardson. Because Richardson's only really defined in 1D, I'm not clear. People don't really do it in multiple dimensions, so I didn't want to draw that comparison. But yeah, you're right. I think that we've not assumed anything which would alleviate this cursive dimension, so it should appear somewhere. Yes, please.
How do you interpret this if you have a smooth function and you can choose a smooth kernel? So you get an infinite exponent s?
Yes, so you can't just plug in s as infinity here, because that would ask for n to be infinity as well due to this restriction. So what we have to do is be a bit more careful. What we do is we take this error bound here. Oops, sorry. then we ask how big sorry, I think my battery's died in this. We ask how big can we make S for our given value of n, and then we very carefully take limits. So the catch is that this constant here is also S dependent. So we somehow need to have a more explicit dependence on that constant than take limits in S very carefully. So we've done that, and I just didn't include the result on the slide, but you can get a result which basically ends up with, instead of an S here, you end up with something that depends on how much data you have. So there's this general idea that to exploit smoothness, you need more data, which sort of makes sense. So the acceleration you get then depends on n as well. Yes, Mate?
Yeah, well, maybe related to my previous question, but so this here, so you assume that you have perfect knowledge of B, like B, this one.
Yes.
And so any thought about the situation where B is specified in some sense?
Yes. So if B is misspecified in a good way, where it's still an upper bound, it's just not a very good upper bound, then everything's fine. If B is misspecified in a bad upper way, then a bad way, as in it's overconfident or something, then this could be a big problem. If you're estimating B, things can still be okay. I won't have anything in the slides about this, so we can maybe talk later. But we've got a one-sided result which says that if you estimate B using maximum quasi-likelihood, then that will it's slightly technical, and I don't know if I want to try and unpack this now because I'm probably mess it up. So maybe we could have a little chat in the coffee break about this. But we've got some partial results. Yeah.
Is there a way to set this prior so that you exactly recover Richardson, like classical Richardson, in the posterior mean?
Yes, but it gives you uncertainty of 0. So you take the kernel to be like a polynomial kernel. But as soon as you condition on all the data, then the uncertainty vanishes. So you can do it, but it's not very useful. Yes?
What's the dependence on n? Is that interesting?
On n?
Yeah.
So n just needs to be big enough, and then this holds for all h as h goes to 0. So if you're interested in getting like an additional 3 orders of acceleration, then this condition here says how big n has to be in order for that to happen. So S would be 3. This would be something like 1 over 10 or something. So then we need 10 data points. But that 10 data points is sufficient for this error bound to hold as h goes to 0. So we know that 10 is enough, and if we take h to 0, then we will have this additional 3 orders of convergence. So there's not an issue with scaling in n particularly. It's just got to be big enough that that inequality constraint on the box field is satisfied. I should also add that this is just theory, and in practice, we seem to be able to get away with n that's not as big as this requires. So I'll show some results later where I think n was sort of 5, but this said we needed n to be like 7 or 8, but things still worked. I think that's just due to the way that we constructed the proof rather than anything fundamental. Okay, so let me move on from this and show you an illustration that backs up this theory. So I'm going to use finite differences because they're probably the simplest example of a non-trivial numerical method that fits into this setting. And actually also, Richardson extrapolation is very widely used in finite difference approximation. So suppose we've got some function and we'd like to evaluate the derivative of this function at a point t. One way to do that is use a finite difference approximation. And the one that I'll consider here is called the central difference approximation, which takes the difference between a value of g to the right-hand side and a value of g to the left-hand side of t, and divides by twice the distance of these inputs from t. The central difference method is, in some sense, a nice one because it's second-order accurate. So in our framework, that will correspond to this function b just being x squared. I'm going to take a sequence of finite difference approximations that corresponds to 5 different values of x. So we'll start with 0.2, 0.4, 0.6, 0.8, and 1. And of course, you'd think the best approximation would be when x is 0.2, because that gives you the smallest distance between g of t plus x and g of x. And then to test whether this theory works, I'm going to scale this design by the global scaling h and consider what happens to the quality of the Gauss-Richardson extrapolation estimate as this global scaling h goes to 0. What we get is on the right-hand side, and there's a lot of lines here, so let's just unpack this a little bit. The solid black line here is what you get from using classical Richardson extrapolation. So we've got a sequence of 5 data points. We fit a fourth order polynomial to those 5 data points and extrapolate that to x equals 0. And that gives us an approximation which is good. It converges faster than second order to the derivative that we're trying to estimate. In this particular example that I used to generate these data, we can expect at most 2 orders of acceleration by doing any of these methods. And Richardson gives you that extra 2 orders of acceleration. Everything else that's black with circles corresponds to another member of the classical set of extrapolation methods. And these basically correspond to doing extrapolation with not polynomials, but something else, like a rational function or something. And these things are designed to be more robust than polynomial extrapolation, because of course polynomials can be quite bad for extrapolation. But in this case, the robustness comes with a loss of efficiency. So you don't really gain any acceleration compared to the original second order approximation. And then everything in blue with triangles corresponds to a Gauss-Richardson extrapolation method where we've chosen this generic kernel KE to be a kernel from the Matern family. And all that differs between these blue lines with triangles is the order of the Matern kernel. Okay, so this S is not literally the order of the Matern kernel, it's the smoothness that these kernels encode. And if we encode 0 smoothness, then we get back an approximation which is no better than using just the highest quality finite difference approximation in our training data set. But if we encode the correct amount of smoothness into these kernels, then we suddenly get the 2 orders of acceleration that the theory predicted. And that conclusion also holds if we use a different kind of kernel, but with the same smoothness properties. So this is a class of kernels called Wendland kernels, which have the same smoothness, but are otherwise different. And finally, just out of curiosity, we tried throwing in the Gaussian kernel, because this is, of course, a very popular kernel. And formally, it corresponds to infinite smoothness. It has derivatives of all orders. And what's interesting there is you get the same 2 orders of acceleration, but the constant, the actual error, is a bit smaller compared to all these other methods. So the use of this kernel is not actually supported by any of our theory. Nevertheless, it gives you the most accurate approximation in this case. However, I would recommend using it because the uncertainty it gives you is terrible, which is what I'm showing on this slide here. So what I'm going to plot here is, again, h on the x-axis, and now the relative error, meaning the ratio of the actual error between f of 0 and our point estimate, divided by the standard deviation that comes from the Gauss-Richardson approximation. So, in other words, this ratio is bigger than 1 if, roughly speaking, if our credible set is much smaller than the actual error. And it's smaller than 1 if vice versa. And what you can see is when you use the Gaussian kernel, although the point estimate was great, the credible set was far too small. And the true value of f of 0 was 7 standard deviations away from the posterior mean. But with all of the other kernels, set up with the appropriate levels of smoothness, the credible sets were fine. Perhaps they're slightly too big, but we don't have an overconfidence problem at least, which is the cardinal sin of a statistician. So we've got some sort of reassuring calibration of the uncertainty here. Okay. And how am I doing this? Well, I'm estimating the scale of the posterior using this particular estimator here. And this corresponds to what you'd get if you did maximum likelihood up to dealing with the fact that this K0 quantity was actually formally infinite, so there wasn't technically a likelihood, but this is the next best thing. Now, I motivated this Gauss-Richardson idea by, I motivated the probabilistic perspective on extrapolation as a way to do experimental design. So now I've got a probability distribution over f of 0. I can think about which data points, if I could get them, would most reduce my uncertainty about the quantity f of 0 that I'm actually interested in, and that's experimental design. And experimental design is actually very easy in this Gauss-Richardson extrapolation setup, because we've got an explicit expression for the posterior variance of f of 0. And it depends on a couple of things. It depends on the hyperparameter sigma squared and on some algebraic things related to the kernel and the experimental design. Now, before we start running any simulations, we obviously don't know anything about the hyperparameter sigma. So let's just ignore that, pretend that's constant, and we'll try and maximize this thing on the denominator, which would correspond to minimizing our posterior variance. And if we want to maximize this thing, well, we can do that by brute force relatively easily. So what I'm doing is I'm searching for a design set X that maximizes this, this quadratic form involving the inverse of the KB matrix, subject to some global constraint on the computational budget. So if Cx denotes the computational cost of running the experiment X in the design set capital X, then the total cost of running all of the experiments will be the sums of these individual costs. I'm going to bound that total computational budget by capital C. Then I'm going to look at the optimal experimental designs as a function of capital C. So each row of this picture corresponds to a different computational budget. This is the smallest computational budget of 10 units, and this is the biggest computational budget of 50 units. If I focus on the case where I have no smoothness to exploit, then the optimal experimental design is denoted by these triangles here. What it's doing here is it's saying run the highest fidelity experiment that you can possibly afford using your computational budget. And that's it. And that makes sense, because if there's no smoothness in the underlying regression function f, then we can't hope to do extrapolation. So the best we can hope for is to get the closest evaluation to 0 that we can manage for our computational budget. What I've done to actually solve this optimization problem is just to solve it on a grid of candidate points. So you see there's a small triangle hiding in here. That's basically because I had some leftover computational budget after running this one. I didn't quite have enough computational budget to run this one, so I've just thrown in a cheap experiment for free. But this is really running the highest fidelity simulation that I can. Conversely, if I have infinite smoothness, so if I've got a very smooth function f, I can exploit that by not running any high fidelity experiments, but instead running a whole bunch of lower fidelity experiments and using those to estimate the derivatives implicitly of this function f. So my extrapolation is improved by having more training data in this regime. And that sort of makes sense if you think about analytic functions, for example. It's sufficient to know what an analytic function does on an infinitesimally small interval in order to know what the function does everywhere globally, right? Or within the radius of convergence of the power series. So that's kind of what's going on here. It's sufficient to know about f in the low resolution regime in order to extrapolate well to the high resolution regime. Okay. So this is a priori experimental design, but you could do this in a sequential way as well. You could run the simulator, get some data, update your experimental design, and so on. I'd like to finish by showing one example of this in practice. Well, maybe I should just ask you, are there any questions about anything I've said up to this point before I move on? Yes, please.
In the slide where you compared to other classical methods with the absolute error, yeah, you said that the other classical methods are more robust. Does it mean that there's a set of function f where your Gauss-Richardson is not robust?
So actually, what I was trying to say was these other classical methods here, so Shanks, Germain-Bonne, BL, they're more robust than Richardson, in the sense that Richardson extrapolation is polynomial extrapolation. But some of these others, I forget exactly which, they differ in terms of the basis functions they use to build the extrapolation. And the idea is that if you use something like a rational function, for example, then that extrapolates in a bounded way, it doesn't explode. So that's the idea of these alternative classical extrapolation methods. As far as the Gaussian Richardson stuff goes, extrapolation is robust in the sense that we're not using polynomials, we're using Gaussian process mean functions, and they are, at least in the well-specified sense, that setting, they're going to be non-explosive for these. So I've not got a very formal statement, but the Gauss bit is regularizing the Richardson bit. Do you see what I mean? Yes.
Quick question. So pattern with S in 0 means this is Laplace kernel.
So this is Matern with that corresponds to smoothness 0 in our framework. So that would be Matern a half in the usual terminology. Yeah. Yeah. I just wanted to match the S's to the theory. So I know it's a little bit different to the standard way of describing a Matern kernel. Okay. So I'll just finish then by showing you an example of this in practice. This is a case study that is in partnership with the biomedical engineering group that, when we started this project, we're at King's College London, and at the end of this project, we're at Imperial College London. It's to do with cardiac modelling, and there's no grisly details in this talk at all, but this is the model. It corresponds to a whole bunch of differential equation type models that are strung together in quite a complicated way. For the purposes of this case study, I'm ignoring a lot of the complexity and just focusing on what you might expect to be the main sources of discretization error. So there are two of these. One is that this model of a human heart is spatially discretized for simulation. And what I've shown here are spatial grids of different fidelities, starting at 1.7 millimeters and going down to 0.4. And the second source of discretization error is time stepping. So this is the dynamical model. It's actually simulating a moving, beating heart. So there's some dynamics, and we discretize those in time for the purposes of simulation. So I'm going to suppose that there are two levers I can pull, spatial resolution, time resolution, and I'm going to try and set these in some way to get the best approximation of what the mathematical equations tell me the human heart should be doing. Now, this is something that's actually very difficult to do in practice, because you can't do numerical analysis for this. So there's no theory that tells you how to balance the contributions of these two error sources. And you don't have a ground truth to compare against. So in practice, the engineers that build these models, they've got some rules of thumb. Right? So they say spatial discretization should be this or smaller, because 0.6 millimeters is the scale of the tissue, and we know there's some dynamical processes that happen at the tissue level. So those need to be properly resolved, and provided that you're at least this small thing should be okay. That's their reasoning. Time stepping, there are also heuristics for this. But you can imagine that for a very large piece of code where there are very many levers that you need to set in some way, actually deciding how to set these things is very, very difficult. And one of the potential benefits of this methodology is that the experimental design framework gives you a way of setting these automatically. So you run a bunch of low-fidelity experiments, you try and estimate the importance of the different levers, and then you can design an optimal set of experiments that balance the different aspects of discretization error within the framework. So these models are very expensive to simulate, and if we look at this most spatially resolved model here, that takes about 4 hours to simulate one heartbeat. So it's not real time. It doesn't sound too bad at 4 hours, but that's 4 hours of 500 calls on the UK National Supercomputer Archer. So this is a non-trivial simulation to run. And the hope long-term for these is that these are going to be patient-specific heart models that are used to inform clinical decisions regarding where to do surgery, right? So these are going to have to be accelerated in some way if they're going to become personalized. So one of the aims here is to say, can we simulate from these models at a reduced computational cost? Or can we get a more accurate simulation for the same computational cost? So what is computational cost in this case? Well, it encapsulates a few different things that have to happen. You've got to set up the model in some way. You've got to assemble the systems of equations that get solved within each time step of the iterative numerical method. And you've got the time that's actually required to solve these linear systems of equations. This is a sort of like a non-linear PDE. You time step, and at each time step you solve a system of linear equations, and you move to the next time step. And the main contributor to the overall computational cost in this case is the assembly time. So this is actually something that we wouldn't typically be talking about in a PN workshop, right? So PN normally says, okay, you've got the problem, how do you solve it? So we're normally talking about solver time. But actually, in this case, assembly time is the big deal. So if we can work with coarser spatial meshes and bigger time steps, then that's going to massively reduce the assembly time because these linear systems are going to be smaller. So the multi-fidelity angle on extrapolation becomes quite relevant to these problems here. Okay. So as I mentioned before, we need the spatial resolution to be small enough to resolve the tissue level processes that are going on, and the time steps to be small enough to resolve the dynamics that happen on those scales. So typically they would work with a default set of resolution parameters that's something like this. So 0.4 millimeters of spatial resolution, 2 milliseconds of temporal resolution. And as I mentioned, the cost of this thing is quite big. So here's what we do. We start out by running a set of low fidelity experiments in order to get approximate values for our Gaussian process parameters. So on this plot here, x1 is going to be the spatial scale in millimeters, x2 is going to be the time scale in milliseconds, and these circles here correspond to our low fidelity experiments that we run in sort of phase 1 of this setup. So here we've got a coarse spatial grid, but a reasonably small time step. Over here we've got a fine spatial grid, but a big time step. So all of these experiments here are relatively cheaper compared to the ones down here. We use the cheap experiments to estimate the parameters of our Gaussian process. Having estimated the parameters of our Gaussian process, we do experimental design. And experimental design tells us which experiments to run down in this regime here where things get expensive. So step 2, phase 2 of this approach, says, okay, we've identified these triangular experiments as ones that we should consider running if we are then going to use Gauss-Richardson extrapolation. So these are an optimal experimental design for Gauss-Richardson extrapolation, as it were. We haven't got a ground truth to compare against here, so what I'm going to do is I'm just going to use this star in the bottom left-hand corner as our ground truth. And this is sort of like the highest fidelity simulation that we can run in a reasonable amount of time. And I'm going to compare that to what we would get if we used, say, default settings that are used by the biomedical engineers at the moment. Okay. So this is slightly more accurate than the default. Everything in this training set here is no more expensive than running this default simulation here. So what I've done is I've run a bunch of experiments that are cheaper than, or I think in this case strictly cheaper than this experiment, although the total cost of running these may be greater, although they can be parallelized. That's the setting. And here's what we get. What I'm going to do here is plot the error of the Gauss-Richardson extrapolation estimate against the error of the default method that engineers are using at the moment. So if this ratio is less than 1, then we've got a more accurate approximation. And if it's bigger than 1, we've got a less accurate approximation. I'm going to consider this relative performance as a function of the computational budget that we give to Gauss-Richardson. So C is going to be our total computational budget. Over here, we're spending more in total compared to the default approach, but we're doing it in parallel. So the actual runtime is no greater than the default approach. And over here, we're spending less than the default approach and doing a small number of experiments. So basically, you can kind of see, for these 7 different scalar values which correspond to clinically relevant quantities of interest, I won't go into any of the biological details, we do worse when we have a small computational budget, capital C, and we do better typically, although there's one exception, when we have a larger computational budget. So that sort of makes sense. We've got an automatic way to design how to trade off the spatial and temporal scales, and provided that we have enough of the training data to train a GP, we can extrapolate well to get an approximation that's more accurate than just using the highest fidelity approximation that was in the training data set. It's a bit difficult to look at these scalar quantities, so this is the final slide I have on this, which is looking at the temporal output of the cardiac model. There's 4 different temporal quantities of interest here which correspond to the volumes of the 4 different chambers of the heart during the simulation. And this is the multivariate output situation that you asked about. So here, the solid black line is our ground truth. The dashed black lines correspond to simulations that were part of the training data set here. And you can see that some of these simulations are really quite different to the ground truth because either the spatial mesh width was too big or the time step was too big. But they can still provide useful information to Gauss-Richardson extrapolation. So the blue triangles here correspond to the experiment using the default settings that the clinicians currently use, and the red circles correspond to the extrapolated Gauss-Richardson approximation. And what you can see is in all of these cases, the Gauss-Richardson extrapolation is more accurate, generally speaking, through time, compared to the approximation that corresponds to just using the default settings. And just to repeat, we're using here training data that were no more expensive to run than the default experiment, although we did require more than one of them. So there was more computation overall, but it was parallel. And this seems to have worked in this case very nicely. It's sort of hard to say with scalar quantities whether you're doing well or not, because, of course, by chance, this might actually be quite a good approximation. It's very difficult to say when you've got one number, but you can see a consistent trend here temporally that the Gauss-Richardson extrapolated curve is more accurate than the default curve that the clinicians are currently using. So that's everything I've got to say. Let me just say a few remarks to wrap up. The first one is that I think this black box framework has value, particularly in cases where it's not obvious how to construct a standard probabilistic numerical method. I think eigenvalue problems are maybe sort of the boundary where it might be possible with enough effort to construct a standard method, but things like this cardiac model is totally impossible. So we'd need something more black box for these models. The way that we made this work was we just totally avoided nonlinear information. That was the fundamental problem. We avoided it by just treating the numerical method as a black box. And this is not intended to be a competitor to probabilistic numerics. It's to complement it in scenarios where it's hard to design bespoke probabilistic numerical methods for specific numerical tasks. If you're interested in what I presented today, there's a paper that came up on arXiv in January called Probabilistic Richardson Extrapolation. And there's a few other things in the paper that I've actually mentioned in response to some of the questions already. So one is estimating the convergence rate in settings where you don't know it. We've got a little bit of theory for that. We've got some discussion of the case where the thing you're interested in has additional dependencies. So for example, in the cardiac model, there's a whole bunch of scientific parameters that actually in the clinical setting would have to be trained against patient-specific data to make the model realistic and applicable to a particular patient. So it turns out you can fold in additional parameters quite easily into the Gauss-Richardson framework, basically by augmenting the input to the covariance kernel with an extra input. And multivariate quantities of interest. We've seen some of this already. There's some useful things that you can do involving Kronecker product structure to simplify the algebra in these cases, and so the paper goes into more detail about that as well. I'd just like to thank all of the authors that contributed to the work that I've talked about in this talk, and most of all, I'd like to thank all of you for coming along and listening to my talk this morning. Are there any final questions before we wrap up? Yes, Philip.
So I really like this ability to wrap something around the existing classic numerical method because it's often a problem like this you can automate an article. But I wonder whether there's also a message sort of the other way around from the information theoretic perspective that when Richardson extrapolation works, or when Gauss-Richardson extrapolation works, that it actually says something about some kind of inefficiency of the classic method. So in a statistical setting, right, we would usually say if you have a Bayesian estimation method that produces a sequence of estimates that are predictable, right, that are smoothly changing towards some final value, then that means that the initial prior was, or the model was somehow badly chosen, right? That you could have predicted more, right? You could have been more efficient, could have made more use of the data that was collected. So, have you thought about this? Is there basically a message in, like, that the ideal numerical method people should be using is the one where Gauss-Richardson extrapolation doesn't work because it basically produces white noise as its estimates?
Yeah, I think that's right. So this is something that of course people know in numerical analysis, and people have used this idea to construct new numerical methods. So I think the easiest example of this is the trapezoidal rule for numerical integration. It's very good and so on, but it only exploits a certain amount of smoothness. And if your true integrand is much smoother, you can do better. If you do Richardson extrapolation on a sequence of trapezoidal approximations, you actually recover the Romberg methods for integration. So you can either think about that as improving an existing numerical method or defining a numerical method to be the output of extrapolation on a simpler numerical method. So I think what you're saying is exactly right. And whether you want to call this thing a numerical method or extrapolating existing numerical methods is sort of a philosophical distinction. But yes, you're right. One of the advantages, of course, is if you can't know for sure that the thing you're trying to approximate has a certain level of smoothness, then you can be safe and use the simpler numerical methods that don't encode the smoothness, but then see in this sort of post hoc way whether you can get any more by exploiting any residual sort of smoothness that might be there.
But if there's not enough smoothness, wouldn't you expect the extrapolation not to work very well?
Yes, but it shouldn't do worse than you would have done otherwise.
I see.
Can you show a slide about this estimator of this f of 0?
So which one, sorry?
Beginning of the presentation is the
Oh, sorry. I don't know how to do that.
GP posterior mean estimate of this f of 0.
So there should be a better way of doing this. This one here.
Oh, yes. And you take this limit of this K0 going to infinity, right? So, and my question is, if you fix K0, not take the limit, but does it still make sense? Does the estimator still make sense?
Yeah, everything still works. You've got slightly more confident posterior because you put a bit more prior information in. But everything still works totally fine. It's just then this choice of 0 here becomes, actually that's probably fine as well. Yeah, it should all work. I was very reluctant to commit to a choice of scale for the prior, so that's why I just removed it. But yeah, you can use it. It actually makes some of the calculations much simpler if you're happy to work with K0.
So there seem to be no more questions. Then let's thank you, Chris.